Welcome everybody back to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from IIT Hyderabad. So last class we began with a very interesting topic. We began the second part of our course. Let us try to recall what we had studied the last time around. We saw how by having passive two-terminal elements as non-volatile storage devices, we can effectively bridge the gap between DRAM main memory and NAND flash, which is the main storage. And these passive two-terminal elements can be known as storage class memory or even ENVMs, electronic non-volatile memories. Also, we saw how the development of the memristive device took place both theoretically and the practical demonstration by HP Labs. We saw that this memristive device is nothing but a two-terminal passive memory element. And we also saw why the pinched hysteresis of the memristor gives us this memory effect. We also defined some very important terms such as HRS or the high resistance state, the LRS, which is the low resistance state, and the transition between HRS to LRS, which is also called the set process, and the transition back from LRS to HRS, which is known as the reset process. So in today's class, we are going to ask the question, what is the basic physical mechanisms by which this repeatable switching takes place in memristive devices? But before going to that, I would like you to know that although in the previous slide, we saw that the behavior of a memristor is more like a smooth curve. If you remember the first memristor that was developed by HP Labs, that had more like this dotted sudden switching. So primarily what I'm trying to get at is there are two kinds of memristive behavior that we see. One is called digital type memristor or digital memristor, and another is analog type memristor. Before we talk about physical mechanisms, it might be valuable to delineate both these types of memristor action. So we begin by understanding the digital memristor. As you can see, this digital memristor, the primary feature is it has abrupt switching in its IV characteristics. So what I mean by abrupt switching is initially you don't see anything happening. It behaves like a high resistive element, and suddenly something happens at something called the set voltage. Remember, the transition from high resistance to low resistance state is called set process. So this transition where this happens is called set voltage. At an abrupt set voltage, the device quickly moves from the high resistance state to the low resistance state. And therefore, there are two clear states that you see, one high resistance state and one low resistance state in this digital type of memristor. It is also important to know, and we will contrast this with the analog type of memristor, that no switching really occurs before the set voltage or the critical V critical. If you take digital type of memristor only to this voltage and return it back, there will not be any transition because you have not applied a voltage which is greater than the critical voltage or the set voltage. Now let us look at the analog type of memristor. As you can see, the analog type of memristor doesn't have an abrupt switching. It has a more gradual switching. And this is the kind of ideal memristive behavior even predicted by Leon Chua. Okay. This gradual IV switching results in several high and low resistive states. How is this possible? That is shown in this particular diagram below. In this diagram, you see by cycling the device through different stop voltages in the x-axis, you can keep expanding the size of the hysteresis or the pinched loop hysteresis. And of course, the hysteresis can be corrected back by cycling in the opposite direction. Now, you would be interested to know that although the analog memristor is what was initially predicted, That is the ideal kind of behavior, and it is very hard to find. Just as you had seen in the first memristive device from HP Labs, most of the memristive devices that we find are generally of the digital memristor type, And why it is important to delineate both of them? Because both have their own unique set of mechanisms, and also they have their own set of use cases. Whereas digital memristors are used for two-level memory, for more traditional forms of computing. Analog memristors are used for more analog computing. And we will study more about analog computing in the coming lectures. So, coming back to our original question, what are the physical mechanism? What is happening in the switching layer or the functional layer, which is leading to this continuous and repeatable switching from the high to low resistance state? And it turns out that it is not one physical phenomena. The same kind of behavior can be explained or can be leveraged by several microscopic physical phenomena. And I have listed a few of them for you. So the first is something called FERAM. FE stands for Ferroelectric Random Access Memory. In FERAMs, what changes is the ferroelectric polarization in the functional layer between the two metallic films. So the functional layer between the two metallic films has ferroelectric properties, means it can either have majority up polarization or down polarization in the dipole orientation of the functional thin film, and that can give you high and low resistive states. The second kind of resistive switching is something called phase change random access memory, or PCRAMs. In PCRAMs, this underlying functional layer goes through a phase change. What is this phase change? The phase change is from crystalline to amorphous material and back. And we will see crystalline and amorphous materials have completely different resistive properties. The third kind of memristive device that is popularly seen is called RRAM, where R stands for resistive switching. Okay, so here what happens, as you can see in this illustration, that there is a growth of filaments or conductive hotspots within the functional layer, which connects the top electrode with the bottom electrode, therefore creating a low resistance state. And when this filament is dissolved, the device goes back to high resistance state. And finally, we have something called MRAM, or magnetoresistance based random access memories, where depending on the magnetic polarization of the two layers, the device can either be in high or low resistive state. So today we begin our study with understanding of phase change materials based RAMs. So this is the second part of our sixth module, where we will go to individual physical mechanisms and see the random access memory technologies that come out from these different physical mechanisms. So let us begin with phase change RAMs. To understand the phase change phenomena, we have to have an understanding of the different states of matter as classified by range of order. Now, when we were even in primary or middle school, we studied that the different states of matter, such as solid, liquid, and gas, is delineated by the intermolecular distance between the two molecules. In solid you have least intermolecular distance, so very tight packing and lot of interaction. In gas, it is very loosely packed. However, within solids, there is another way to classify the states of matter through something called range of order. What is range of order? It is an indicator of how orderly the arrangement or packing of molecules is in a particular solid. So as you can see, there are different packings which you may have heard of from your basic courses. These are your crystalline packing, where the arrangement of atoms is completely periodic across the whole volume. So that is why you say that there is long range order. That means across the solid, there is a periodic arrangement of lattice sites or of atoms. The opposite end of crystalline is amorphous. In amorphous, you do not see any such periodic arrangement. You see, every molecule or atom in this constituent solid is randomly packed. In between is something called your polycrystalline material. Here what happens is there is periodicity with grain boundaries. So see, I have marked out one particular grain. A grain is a collection of atoms where you see some periodicity. And as you can see, grains may be amongst themselves misaligned, but within a grain you see periodic arrangement of atoms. And what is very interesting for our purpose is that in the same material, the ordering of atoms in crystalline or amorphous phase completely affects the electrical and optical properties of the material. So, since we are primarily interested in electrical properties, let's ask the question, what about resistance? How does resistance vary for the same material once it is arranged in crystalline and in amorphous phase? And a little bit of understanding of device physics may tell you that while a crystalline material is expected to have low resistance, an amorphous material is expected to have high resistance. Why is this the case? This is because crystalline material is ordered. So an electron which is going through this crystalline material will go through very less scattering events. But since there is a lot of disorder in amorphous system, an electron which will go through the amorphous system will go through lot of scattering events. And therefore, because the scattering events will be more, the mobility will be less, and therefore the resistance will also be higher. Therefore, because of increasing disorder from crystalline to amorphous system, the resistance of amorphous systems is also more than that in crystalline systems. And this gives us an amazing window of opportunity, especially when we look at eNVMs or storage class memories of two terminals. Why is this the case? Suppose we are able to repeatably switch a material from crystalline to amorphous phase. As we saw that the resistance of crystalline phase is generally much lower than that in amorphous phase. This will result in a repeated switching between LRS to HRS. And this is the primary philosophy of how phase change memory or phase change RAMs work. So the important question to ask is, how is this switching facilitated? Generally, it is done through energy or heat. And what will be very interesting in the context of PC RAMs is that how do we provide this energy or heat using electrical pulses? Okay, so while there is a great opportunity in this area, there are also several challenges that we should discuss before moving forward. So what are the challenges? The first challenge is to identify an appropriate phase change material. Ideally, all materials should show some form of phase change behavior, but most of the materials will not be suited for phase change memories. Why is this the case? This is because whenever there is a transition from crystalline to amorphous state, there will be a energy barrier which you cross through providing this heat energy. So this energy barrier should not be too high. If it is too high, writing into the memory or changing it from crystalline phase to amorphous or vice versa will become a big problem. So you will have to supply a lot of energy, and that will cause a lot of problems in power consumption. However, if the barrier for transition is too low, you will start having retention issues. Why? Because even thermal lattice vibrations will be sufficient to move the state, at least a few atoms or some volume, from amorphous to crystalline or vice versa. So always, as we had seen, there is a trade-off between write, easeability and retention in non-volatile memories. The second is, since the energy will be supplied through electrical pulses, the mechanism of operation is Joule heating. Joule heating is nothing that we have studied in our basic physics. When you flow current through a resistor, I square R is the Joule heating. So the conductivity has to be appropriate to facilitate Joule heating. If the conductivity is too low, enough current will not flow. And if the conductivity is too high, there will not be enough Joule heating. The next important point is the kinetics, or the time between switching from crystalline to amorphous phase must be fast enough. So remember, ENVMs have to play in the regime which is slightly worse than DRAMs, which is roughly 100 to 200 nanoseconds. Also, the difference in the resistance between the crystalline and amorphous phase, or the ratio between the high and low resistance state, should be at least a few orders of magnitude to make sure that your external readout circuitry has enough margin and enough signal to noise ratio. Finally, it is also desirable that the materials that are designed for PCMs are CMOS compatible. Why? Because ultimately they have to be integrated in your CMOS line of processing. So with this understanding, let us have a quick review of the historical evolution of phase change materials. So phase change materials were first discovered by Stanford Ovchinsky in 1968, where he noted in his seminal PRL paper that a variety of semiconductors, mostly compound semiconductors belonging to group 6 and group 5 elements combined with group 4 elements such as chalcogenides, nitrides and oxides, show repeatable resistive and conductive states which can be switched by electrical pulses. However, the first commercialization of phase change materials in the form of chalcogenides was done in optical discs. So most of you might have noticed these optical discs that used to come with older generation of laptops and CPUs. So what the material or the core material that these optical discs or DVD and Blu-ray discs use is actually phase change material. In these optical discs, first what you do is you coat the entire material with a crystalline chalcogenide material which forms the erase state. Now to do programming, you apply very short pulses of 10 nanoseconds, and what you do is you melt the material and convert that crystalline material into amorphous phase. As we saw in the previous slide, the crystalline material will have completely different optical properties as compared to the amorphous material. This is because crystalline material has more order, so the reflectivity will be very large, just like you see in a mirror. However, the amorphous material will have very poor reflectivity. And this is how you were able to write ones and zeros into these optical storage media by checking their reflectivity. Only very recently though, in 80s and 90s, the scientific understanding of phase change materials, especially the discovery of GST, which we will study in detail, which is a ternary compound between germanium, antimony and tellurium, was discovered. It was shown that it is more like a magic material with lot of important properties. And since then, GST and its variants have occupied most of your application space when it comes to phase change materials. Very recently, only in 2010, the idea of trying to use PCMs in solid state drives as eNVMs was introduced, and that is what is going to be the focus of our study. But also interesting to know from our perspective that even neuromorphic computing may benefit a lot from this new era of phase change RAMs. Okay, so with this brief historical perspective about phase change materials, let us ask the fundamental question: how do you facilitate this phase change using electrical pulses? Before that, very quickly, let's recall that an amorphous material is in high resistance state because electron scattering is more through amorphous material, and the crystalline material is in low resistance state. Therefore, the process of crystallization from amorphous to crystalline state is called the set process. This is called set because, as we defined in our previous class, the transition from HRS to LRS is set. Quite the opposite is the change from crystalline material to amorphous material. So this amorphization process is therefore known as the reset process. Okay, so how does this happen? To understand this, we need to look at the energy landscape of crystalline and amorphous phase. So on the x-axis, we have different states, and on y-axis, we have the energy configuration of these states. As we have been studying in our basic physics lectures, why a solid forms into a crystalline lattice, because that is the global minimum of the arrangement of atoms. That is why crystalline lattices form, and this is what is indicated even in this diagram. As you can see, this is the global minima. The crystalline phase is the global minima, whereas the amorphous phase is also a minima, but it is a local minima. So with this in mind, let's try to understand the set process. So how will you do the set process? The set process is the process of crystallization, from going from the amorphous phase to the crystalline phase. As you can see from this energy landscape diagram, to go from amorphous to crystalline state, the barrier that you have to cross is not very large, but you will have to wait for much longer time. Why? You give it a little bit of heat, this amorphous state, a little bit of heat, and you allow some time for the atoms to organize into a periodic lattice. To strengthen our intuition about this, I have taken a video. So what we will see in this YouTube video from Steve Moll's channel is how amorphous material, you see there are a lot of amorphous material. Basically, this is simulation done with small steel balls. How when you give it enough energy, slowly from amorphous state, they will go into more ordered crystalline state. So let us start the video. As you can see in the video, when you give this amorphous material a little bit of a shake or a little bit of energy, the different grain boundaries, as you can see in a zoom up now, the different grain boundaries are coalescing, and slowly it is going into its least configuration state, which is your crystalline state. So if an amorphous state is given a little bit energy, it goes from its local minimum to its global minimum. Now let us look at how do we do the reset. As you can see from the energy landscape diagram, the jump from the crystalline state to the amorphous state is a rather big jump, and therefore you have to give it much more energy. So basically, to go from the crystalline state, which is a global minima, to amorphous, which is a local minima, you have to give it a lot of energy. You have to jolt the system out of its least configuration state, and not only that, you have to immediately quench. Means you have to immediately remove the source of heat or source of energy. If you give it enough energy and allow it to settle down, it will come back to its crystalline state or it will recrystallize. But if you give it enough energy and force it to immediately cool down, there is a chance that it will go to its amorphous phase. And to give an intuition of that, just imagine that this lady was holding a lot of tennis balls in a crystalline packing. They were all packed very well together. She suddenly gave a jolt to it by flinging them in air. And now what I have done is, I have created a snapshot after giving this jolt. I have removed that energy, I have frozen it. So what will happen is, earlier what was in a crystalline or ordered manner, because of this jolt, what has happened is it has become disordered, and therefore if you freeze the frame now, it will go back to its amorphous state. So this is the understanding. So set process requires you to give less energy, but for a more longer period of time, whereas your reset requires you to give more energy and then immediately quench it. Now, with this understanding, from the energy landscape diagram, let us see how using Joule heating, this energy is given to a phase change memory in both set and reset cycles. So before we go and understand that, it is important to define two terms. One is called the crystallization temperature and another is the melting temperature. What is the crystallization temperature? Crystallization temperature is, suppose you are in amorphous state, how much little bit of energy that you need to give to these atoms in the amorphous state so that they can wiggle around a little bit, enough energy to wiggle around a little bit and reach to its global minima, which is the crystalline state. Whereas the melting temperature, as you know from the process of melting, you give it so much heat that the tight packing between the bonds is broken and it almost goes to liquid phase. In that liquid phase, there is a lot of disorder. If you suddenly freeze it, it will remain in its amorphous phase. And this is what is done using Joule heating as well. So next we will see how the set and reset is facilitated by different amplitudes and durations of electrical pulses. So as you can see from this diagram, the set pulse requires you to apply a long pulse, a very long pulse with very medium amplitude. What should be the criteria for applying the set pulse? It should be just enough to take the material's temperature to just above crystallization temperature and wait for a longer duration so that the amorphous phase becomes crystalline phase. So generally this temperature is in the order of 200 to 300 degrees Celsius with the time of roughly 100 nanoseconds. Whereas the reset phase requires you to jolt the system. Therefore, you only need a short pulse with very, very high amplitude, gives it so much energy that the system goes into a semi-molten state. Not only that, the pulse should be short enough so that there is an immediate quench process which freezes the disordered state back into the amorphous state. Okay, so if you do a very high reset pulse with a very fast quench, atoms get no time to settle in. So the temperature for this generally in GST films is between 500 to 700 degrees and the time is roughly 10 nanoseconds. And from this you can understand while the set cycle will be the limiting factor for the latency of read and write. Why? Because the set pulse is generally much more elongated to give it enough time to crystallize. The reset pulse is what will define how much power consumption happens because the reset pulse is much larger in amplitude. Finally, to do a non-disturb read, as we can see in this black curve, you apply a very small non-disturb pulse through which you can see whether the device is in high resistance state or low resistance state. Furthermore, to optimize the phase change material through the process of Joule heating, we have to ensure that we do a very good engineering both in terms of materials and in device optimization. So the materials optimization and device optimization of PC RAMs is what we will see in our next class. Thank you very much for your attention. See you in the next class.